Alright guys, let's see how we can solve another question from the third chapter of the Meriam textbook, Engineering Mechanics. And in this one, we have this uniform slender bar of length 2r, and the r in here is the radius of that circular part of the system, and the massive M that rests against the circular surface. We need to determine the normal force at the small roller A and the magnitude of the ideal pivot reaction at point O. So we have a pin at point O, which means we have two different reactions, one along X and one along Y axis. So two unknowns so far, and also we have a normal force at point A, which is going to be the third unknown that we're trying to figure out in here. So let's start with the free body diagram of that slender bar. So we're going to have a normal force at point A, which will be along the line that connects A to the center or the radius. So this would be our normal force. At point O, as I mentioned, we have a pin, which we consider one X component and one Y component. And I'm just going to call our X and Y in here. And we're going to have the mass of this bar, which we know has a massive M. So obviously we're looking for the weight. So we're going to have the weight, which would be mass times acceleration of gravity. And the center of gravity would be exactly at the center of this bar, since we have a uniform slender bar in the question. So the center of gravity would be exactly at the center. So the length of the bar is 2r. So we're going to have r on the left side and another r on the right side. So in order to figure this out, we need to figure some angles in here. And if you look at the triangle that I'm highlighting in yellow right here, we have all the sides. We know that AO is 2r. We have this side 1.25r, and the other side would be the radius. So by a simple law of cosines, we should be able to figure out some of the angles. Let's start with this one. Let's call it alpha. And if we want to do the law of cosines, we know that the long side, which is 2r squared, is equal to r squared plus 1.25r squared minus 2r times 1.25r times cosine of alpha. So from here we can find alpha. So we can just divide r squared in here because we have r squared in each of these, so it will be canceled out at the end. So we have 4 in here, 1 plus 1.25 squared minus 2 times 1.25 is 2.5 cosine of alpha. So we can find cosine of alpha in here, which will be 4 minus 1 minus 1.25 squared over 2.5. We have a negative sign in here too. So let's calculate this. So our alpha would be cosine inverse of 4 minus 1 minus 1.25 squared divided by minus 2.5. So this is going to give us the alpha would be 125.1 degrees. And let's call another angle in this triangle, maybe this one beta. And if we just do the law of sines in here, sine of beta over the side in front of it, which is r, is equal to sine of alpha, or 125.1 degrees over 2r. So we can cancel out the r from each side. So beta would be sine inverse of sine of 125.1 divided by 2. So let's calculate our beta. So our beta would be 24.15 degrees. And now that we have these angles, if we want to find one more angle here, this one, maybe we can call this one theta. We know theta would be 180 minus alpha, or 180 minus 125.1, which is going to be 54.9 degrees. So now that we have all of this, it's pretty easy to figure out our unknowns. We can start with the moment about point O, since we have the most unknowns about O and we are in equilibrium, counterclockwise positive. We're going to use our first equilibrium equations. So for finding the moment of NA, we can go with any point on the line of action of NA. So it seems if we go in here, our R is pretty easy to figure out if we consider that the center of this circular path. So if we try to resolve the force NA into X and Y component, the X component won't make any moment, but we're going to have the moment of the Y part, which is going to be a moment clockwise. So we're going to have a negative moment minus NA, and for that we need the angle theta, so sine of theta would be that angle, or sine of 54.9, and the distance would be basically the 1.25 r. And also we're gonna have the moment of the weight, which about O is counterclockwise, so that's gonna be positive mass times acceleration of gravity, and the distance would be the vertical distance to the line of action, or what we have in here, which would be r cosine of beta. So times r cosine of our beta was 24.15 equals 0, and from here we should be able to find the NA. So the r will be cancelled out, and we're gonna have mg times cosine of 24.15 divided by sine of 54.9 times 1.25. So let's calculate this. 24.15 divided by sine of 54.9 times 1.25. So this is going to be 0.892 mg, and that would be the first unknown in this question, or our normal force at the roller. One thing we need to keep in mind is that we have a roller and we are neglecting the friction in that circular surface. So that's why we only consider the normal force. And we have two more equations. We have one force equation, sum of all forces in x equals 0, which we're going to have OX. We're going to have the x component of NA, which would be NA cosine of theta. So NA was 0.892 mg, cosine of theta, which was 54.9, and that's pretty much everything. So we can find OX in here, negative mg times cosine of 54.9, so 0.513. That's going to be OX, and going to do the last thing, sum of all forces in Y. Going to have OY. By the way, the negative sign in here shows that the OX that we assume at the beginning is to the right, it's actually to the left. And we're going to have OY minus the weight, and we're going to have the Y component of NA, which is 0.892 mg. This time for the Y component, we're going to have the sine of theta, and this is our theta, so sine of 54.9. So OY would be basically, if we factor mg, it's going to be 1 minus, so let's calculate this, 1 minus 0.892 sine of 54.9. So this will be 0.27 mg, no negative sign. That shows that our OY is actually upward. And if we want to find the magnitude of at O, we're going to have the square root of OX squared plus OY squared. We can actually take out the mg, 0.27 plus 0.513. Let's calculate this one. Square root of 0.27 squared plus, so our O would be 0.58 times mg. So yeah, that's pretty much everything for this question. Hope everything was clear. Let me know if you guys have any questions, and you guys take care. I'll see you in the next video. Have a good one.